Good day everyone, my name is Ron and let us solve some thermodynamic problems. So this problem is an inspiration to problem 7.31 of Introduction to Chemical Engineering Thermodynamics 8th edition by Smith, Van Ness, Abbott, and Swihart. So this is not actually the same problems as 7.31 but it's a modified problem to accommodate the lecture we will have today. So in this problem, saturated steam at 125 kilopascals is compressed adiabatically in a centrifugal compressor at 700 kilopascals at the rate of 2.5 kg per second. The compressor efficiency is 78%. What is the power requirement of the compressor and what are the enthalpy and entropy of the steam in its final state? To start, let us have the diagram given. So this is the compressor and the inlet conditions is it is a saturated steam at 125 kilopascals and 2.5 kg per second. Next, the outlet is compressed steam at 700 kilopascals and the details of the compressor is that it operates adiabatically, hence why Q equals 0, and its efficiency is 0.78%. The required, how much power is consumed in this process, and what is the enthalpy and entropy of the outlet stream. So to solve this, I will solve it using hand calculation, then I will use DWSIM to justify my solution. So to assume, we need to first assume the details of the system itself. We can assume a steady state system such that the flow rate inlet is equal to the flow rate outlet, meaning 2.5 kilograms per second is existing in the inlet and outlet stream. A constant flow speed, meaning we assume that the fluid is moving at a constant velocity, so no kinetic energy, not really no kinetic energy, but zero change in kinetic energy. Then constant height, we assume that it will be ground level, meaning that there is no change in potential energy. Now the unit operation details for turbines specifically. Work for turbines is not really turbines, but compressors specifically. So work for compressors is consumed. This means that it is positive in nature, not negative. It is positive in nature. And its power is also consumed. So in order to find power, it's just simply multiplying the shaft work by the mass flow rate of the given. Then minimum consumed power is simply the isentropic shaft work times mass flow rate. And unless stated, but it is already stated by its adiabatic condition, Q equals 0. So this is satisfied. And the efficiency of the compressor is simply the minimum power consumed over the actual power consumed, or this is equal to the shaft work at isentropic conditions, over actual shaft work conditions. Then we cross out the mass flow rate terms. We will get that the efficiency is also equal to the isentropic shaft work over the actual shaft work consumed. Then to start with this handheld solution, we need to do a steady state open system energy balance, one inlet, one outlet. These three are all assumed to be 0 and shaft work is positive. Hence why the formula for shaft work for compressors is the outlet enthalpy minus the inlet enthalpy. Then for isentropic conditions, the outlet enthalpy at isentropic conditions minus inlet enthalpy equals the shaft work at isentropic conditions. Then, to find the inlet conditions of water, saturated vapor. So take note, the water is saturated vapor and we already know its pressure. That means it is easy to find the properties of saturated vapor at a specific given pressure. So, using the thermodynamics properties table obtained from the steam table of SBAS 8th edition, the book of where this reference is, I found out that the enthalpy of water is 2685.2 kilojoules per kilogram and 7.2847 kilojoules per kilogram per Kelvin. And this is the steam table proof at 125 kilopascal. This is the enthalpy at saturated vapor. This is the saturated vapor line, 2685.2 and 7.2847 kilojoules per kilogram per Kelvin. Next, we need to find the outlet conditions at isentropic conditions. So we know that water is compressed vapor. This doesn't help us that much, but we know that the pressure is 700 kPa. Since we assume that it is isentropic, this means that the entropy at the inlet is equal to the entropy at the outlet. That is, S1 equals S2S or entropy at isentropic condition equals 7.2847 kilojoule per kilogram per Kelvin. So how do we find the enthalpy using these data? So we need to find at 700 kPa and this entropy value the enthalpy at isentropic condition. So we just need to do a simple interpolation. We cannot do a quality method because this value does not stay in between the saturated at 700 kPa. This entropy value does not stay in between the saturated liquid entropy and the saturated vapor entropy. Hence why it is simply a interpolation between this line and this line, the saturated vapor and the first line of the first given temperature of the steam table. So doing a single interpolation using these values, we get that the isentropic enthalpy is 3058.6993 kilojoule per kilogram. Then I found out that the actual enthalpy at the outlet using the definition of power consumed. So remember that the power consumed using the efficiency has this formula. Then we found out that this formula can be derived, meaning that enthalpy outlet minus enthalpy inlet. Then for isentropic conditions, the enthalpy of the outlet is at isentropic conditions while the enthalpy of the inlet is the same. So by substituting this formula into this formula and this one, we already know the efficiency, we already know the isentropic conditions at the outlet, we already know the inlet conditions enthalpy as shown earlier in the steam table. We found out that the actual enthalpy at outlet is 3164.0452 kilojoules per kilogram. Then finding the actual power requirement is simply multiplying the actual shaft work times the mass flow rate. Actual shaft work is simply actual enthalpy minus enthalpy of the inlet times the mass flow rate overall. Multiplying and substituting, we got a total power output, the total power consumed in the compressor is The total power in the compressor is 1197.1130 kilowatts. Finding the actual entropy at the outlet using the calculated enthalpy and known pressure, so we just need to simply interpolate in these values. So we already know the actual enthalpy, which is H2, and we just need to find the actual entropy. So it's just simply a single interpolation, still at the same 700 kPa mark. So the enthalpy lies between here. Enthalpy is 3164, so here. Then the entropy is also around here in the middle. So using an interpolation, we found out that the actual enthalpy is 7.4741 kilojoule per kilogram per Kelvin. Then let us solve this problem using DWSIM. So going to DWSIM, create a new process model, wait for it to load. Then we need to specify our conditions of the system. So we have steam, but it's just another word for water. Then only water is concerned, so we'll just put here next. Then we'll only use steam table since it's only water, as I said, and add them here. Next, the system of units. Let's define our system of units, customizable. Pressure is kPa, so put it here, and the pressure difference is also kPa with respect to it. Then the mass flow rate is kilogram per second. Then lastly, the temperature is Celsius. Since the steam table at SVA is at Celsius, then we will also input it as Celsius. Finish. Then we will go to pressure changers, compressors, and DWSIM will automatically provide the streams for us. Then let's first rename it properly. So this is the inlet stream, and this is the outlet stream, and this is the energy consumed. This is the compressor, and it requires energy to move or to operate. First, we need to find the initial pressure 125 kPa and 2.5 kilogram per second. But we need to know the temperature. How do we know? So what temperature should we use for the inlet saturated steam? Well, since we already know that the steam is saturated by nature and we already given its initial pressure, then using the saturated steam table or just a superheated steam table, we can determine its saturated temperature corresponding to its saturated pressure. With that in mind, its saturated temperature going to this steam table, its saturated temperature. So this is the pressure 125 kilopascal. Under it is its corresponding saturated temperature. Its saturated temperature is 105.99 Celsius. So we'll put here 105.99 Celsius. Okay, then the compressor details. So it operates adiabatically. Then its efficiency is at 78%. And lastly, its outlet pressure must be 700 kPa. There you go. And we have now our results. So from our hand calculation, the outlet enthalpy is 3164. For this DWSIM, the outlet enthalpy at same unit is 3153.85. Next, the total consumed power is 1197.11. Here it's 1172.28. And lastly, for the entropy, actual entropy of the outlet, it's 7.4741, while for the simulator, it's 7.4579. So, it's the same 1.172.28, 3153.85, and 7.45798. Comparing the answers, from my hand calculations, these are my hand calculation results, and these are from DWSIM using a percent difference formula. So let me go back to my previous problem. The percent difference formula has the form calculated minus simulated absolute value over the average of the calculated and the simulated times 100. So using the same formula, I calculated that in terms of enthalpy between the hand calculation and the DWSIM, it has a 2.10% difference. For enthalpy outlet, it is a 0.32% difference, and an outlet entropy, it is a 0.22% difference. And going by the rule of thumb for scientists, a percent difference less than 5% is an acceptable answer. And therefore, since my percent difference is less than 5%, and it is very, very similar to how DWSIM solves it, this means that we understood the theory and lessons perfectly. Thank you, and good day.